Okay, we're going to compare some triangles. We want to be able to identify similar triangles. And we'll also use geometric means. Of course, the reason why it's in this unit is that the similarity is going to occur within a right triangle. So if I start with a right triangle, construct an altitude. There's actually three triangles in the picture now. The original large one, and then a medium-sized one, and a small one. There I've got the medium-sized one drawn in red, the small one drawn in blue, separated out so it's a little bit more clear. So I've got the original triangle, which was ABC, and then two new triangles. I can make three different similarity statements because I can take any two of the triangles and they're similar to each other. Now, I tend to get a little bit crazy trying to get all the corresponding parts to line up, all the letters line up. So I take a look at this slightly differently to set up the proportion. All right, so first I will look at the small triangle, right? Instead of calling it EGH, I just call it the small triangle. And then instead of looking at like side EG, I say, hey, that's the hypotenuse. And instead of looking at side GH, I say, hey, that's the long leg, right? If I'm looking at the small triangle, the hypotenuse is 3, the long leg is X. Now I'll look at the medium-sized triangle. So I'm not going to try to figure out what letter corresponds with what letter. I'll say, okay, in the medium triangle, I know the hypotenuse is 4. And now the short leg happens to be X. Well, that doesn't help me out because I've only got the hypotenuse. I can't set up a proportion with only one corresponding part. So let's look at the large triangle. Well, on the large triangle, the hypotenuse is 5. The long leg is 4. And the short leg is 3. Okay, now I'm in business because if I look at the small triangle and the large triangle, not only do I know the hypotenuse, but I also know the long leg. So there's my proportion. The small triangle hypotenuse compares to the large triangle hypotenuse. The same way the small triangle long leg compares to the large triangle long leg. 3 compares to 5 as X compares to 4. Cross multiply. 3 times 4 is 12. And 12 divided by 5, 2.4. Now, some of you perhaps noticed that, hey, with the medium triangle and large triangle, we've got the hypotenuse and the short leg. Couldn't I have compared the medium triangle and the large triangle using the hypotenuse and the short leg? Yes, I could have. Proportion looks a little bit different now. All right, I didn't have the fraction 4/5 before. I didn't have the fraction x over 3 before. But when I cross multiply, oh my goodness, I still get 5x equals 12. 12 divided by 5 is still 2.4. So as long as I am consistent when I set up my proportion, I will get the same answer. I'll get the correct answer. For me, it's just easier to think about the small triangle, the medium triangle, the large triangle, and think about the hypotenuse, long leg, and short leg, instead of trying to get the corresponding letters to line up correctly. So let's look at one of these again. Small triangle. Long leg is X. Hypotenuse is 5. Medium triangle. Hypotenuse is 12. Short leg is X. Again, only one corresponding part, and that's the hypotenuse. I cannot compare the long leg to the short leg. Grab the long edge triangle, and once again, I can compare the hypotenuse from the small triangle to the large triangle. I can compare the long leg from the small triangle to the large triangle. So there's my comparison. The small triangle hypotenuse compares to the large triangle hypotenuse. The same way, the small triangle long leg compares to the large triangle long leg. Substitute the values that I know. Cross multiply. And I'm going to round this off to the nearest tenth. 60 to divide by 13. If you try that on a calculator, you're going to notice there are a lot of digits behind the decimal point, so I'm just going to round it off to about 4.6. Of course, if you notice the short leg matches between the medium and large triangles, I could have taken that route. But again, I set the proportion. It looks a little bit different. Right? I've got 12 over 13 instead of 5 over 13. I've got x over 5 instead of x over 12. But when I cross multiply, I still end up with 13x equals 60. As long as you're consistent and set up the proportion correctly, you'll get the correct answer. This time it looks like I'm going to have to use the small and the medium triangles. Because in the large triangle, all I have is the hypotenuse. So small triangle, I know the long leg is y, the short leg is 5. Medium triangle, long leg is 8, short leg is y. All right, I can't use the large triangle. I don't know either leg. I only know the hypotenuse on that. But I'm in business here. I can compare long legs and short legs. Small triangle long leg compares to medium triangle long leg. Small triangle short leg compares to medium triangle short leg. So y compares to 8 the same way 5 compares to y. Cross multiply. Well, isn't this unusual? Y squared. Square root of 40? Well, I don't want to just grab a calculator. Let's try to do this one exactly. 4 times 10 makes 40. I can take the square root of 4. I get 2 root 10. Interesting. I wonder what is shaking here. Y times y made y squared. This brings us to the geometric mean. You're used to thinking that the mean would be like the average of numbers. Well, when you're doing that, you're actually finding the arithmetic mean. Right? If there were 6 numbers, you add them up, you divide by 6, that'd be the arithmetic mean. Instead, we're going to be looking at the geometric mean. Notice with the geometric mean, it's always just 2 numbers. Right? I can't use a long list of numbers the way we're used to doing to find an average. And sure enough, look at that. We just saw that proportion on the previous question, basically. Right? X squared equals A times B. So X has to be the square root of A times B. So for an arithmetic mean, you would add all the numbers up, and then you'd count, and then you take the sum divided by how many numbers you had. Where with a geometric mean, you just have 2 numbers, you multiply them, you take the square root. Again, here I want exact values. So let's do a few examples real quick. What if I give you 3 and 12? Well, 3 times 12 is 36. Square root of 36 is 6. There's your answer. The geometric mean of 3 and 12 is 6. What if I give you 6 and 15? Well, multiply 6 times 15 and you get 90. Square root of 90. What's my best choice here? 9 times 10. Square root of 9 is 3. Square root of 10, I'm stuck with that. So the geometric mean of 6 and 15 would be 3 root 10. How about 12 and 15? Multiply 12 and 15 together. I get 180. Now this might not be so easy in my head to figure out which pair of numbers to use. So if it's not quite so obvious, right? I mean, 90 was pretty obviously 9 times 10, but what am I doing with 180? Make a factor tree. Well, it's 10 times 18. Of course, neither one of those numbers is a square. But 10 is 2 times 5. 18 is 2 times 9. And of course, 9 is 3 times 3. So the prime factorization, there's a pair of 2's, a pair of 3's, and a leftover 5. Of course, 2 times 2 times 3 times 3 is 36. So I will use 36 times 5. Square root of 36 is just 6. Square root of 5, I'm stuck with, right? That's the factor I could not pair up on the factor tree. It looks like the cows are coming home. So the IXL is Q2. The converse of the Pythagorean theorem. Again, you can look at geometry or level L. Converse of the Pythagorean theorem, of course, is actually reviewing a skill that we looked at previously.